Okay, I'm Hank, and today I will introduce observations of turbidity currents in a small slope-confined submarine canyon in the eastern Mediterranean Sea. And submarine canyon can be classified into three types. Type 1 is not shelf incising and river associated. Type 2 is not river associated but shelf incising. Type 3 is river associated and shelf incising. And what's the significance of submarine canyon? It's a channel between the continental shelf and the deep sea, and it can guide the gravity flow into the deep floor. And look at the top picture. It's type 1. And when the canyon is formed at the beginning, it's type 1. And it just erode the continental slope. And when it erode upward and erode the continental shelf, it's type 2. And when it continue to erode and encounter a river, it's type 3. Okay. And this is the submarine canyon around Taiwan. The SSC is Shoushan Canyon, and it's type 1. And KHC is Kaohsiung Canyon, and PHC here is Penghu Canyon, and FLC here is Fangliao Canyon, it's type 2. And KPC is Gaoping Canyon, it's type 3. And what is turbidity currents? Turbidity currents are gravity flows, and generally, maximum velocity appears at the advancing front of the turbidity currents. And the formation of turbidity currents is very important. The turbidity currents may trigger by any mechanism which introduce lots of sediment into the seawater. And this is the study site. It's called Bat Galleon Canyon, and it's 5 kilometers long. And this canyon starting near the shelf break at water depth of 105 meters. And it reached a water depth of 830 meters at its opening. And this canyon is type 1. And the time is 249 days between October 25, 2019 and June 30, 2020. And this is the canyon. And we enlarge the map. Its location is here. And why do we study this type of canyon? Because few observations have been made in small submarine canyons. And we want to know if the temperature, salinity, and other changes during turbidity currents in small canyons are similar to those in large canyons. And this is the measurement tools. We have two stations. The shallow station is at 350 meters under the sea, and the deep station is 710 meters under the sea. And this is sediment trap. This is turbidity meter. This is ADCP. This is thermometer. It's CDD. And a turbidity meter, it can detect suspended particle in water, and sediment trap can collect settling particle for an analysis. And thermometer can monitor the water temperature. And ADCP can measure water currents, and CTD can assess water salinity, temperature, and depth. And sediment analysis. The sediment was rinsed in distilled water, then shaken and decanted to remove the salts. And we repeat this action 3 times and dry the sediment. We can use the dry sediment to calculate the mass flux. The G is gram, and M is meter, and D is day. And the turbidity data from the OBS sensors was converted to suspend sediment concentration after recovery. And what is OBS? It's called optical backscatter sensor, and it's at the bottom of the CTD. And the OBS can measure turbidity by detecting the amount of light scattered by suspended particles in the water. And this is the result. It's at shallow station. The gray area is winter storm, and the x-axis is time from November 1, 2019 to July 1, 2020. And we look at the temperature in the autumn. It's stable, but in the winter it's fluctuated. And we can find the highest and lowest temperature in winter. And look at the SSC. The average SSC in winter is very high. It demonstrates the turbidity currents can bring lots of sediments. And this is current across slope velocity. And the highest velocity and the lowest velocity is measured in winter. And the negative velocity is that the current is upward and the positive is downward. And this is deep station. We can look the highest and lowest temperature in the winter too. And the SSC in the winter is very high. And we can find the current across slope velocity. We can find the highest and lowest in the winter too. This is two winter storm observations. The gray area is the winter storm, and the green line is the salinity. When there is a winter storm, it causes turbidity. The salinity will increase, and the temperature will decrease. And temperature inversion during turbidity events. In general, seawater density and stratification are mainly controlled by the temperature, less by salinity. And turbidity current can transport less dense warm water beneath denser cold water, and such as mudslide. If there is a mudslide, the car will be washed away easily. And assume the blue arrow is turbidity current, and this is called seawater, and this is thermometer. And when a turbidity current flows under the cold water will rise, such like this. And the thermometer measure the temperature will decrease, so that turbidity current may cause the temperature decrease. And this is the velocity of currents. The velocity is vertical. And the negative velocity is that the current is upward and positive is downward. We can see the highest velocity closer to the seafloor and then slower upward. And at this deep station is as same as shallow station. The velocity will slower when the depths rise. And at this depth, sometimes we can find the velocity is negative. It means that the current is upward. And the conclusion is, in a small canyon, the variation in temperatures, salinity, and other parameters brought about by turbidity currents are similar to those observed in other larger canyons. And turbidity can make the temperature decrease, and storms can lead to turbidity currents. Thanks.